depends on the energy scale because of the vacuum polarization. Now, what we are considering this is in case of quantum gravity, because of this fluctuation of the quantum gravity, naturally the Newton coupling depends on the energy. And we want to understand what consequences this may have to black holes. To get the physical effects in the black hole geometry, we cannot talk about the energy scale. This is, but because of the relation between the length and energy due to the de Broglie, the length scale can be related to the energy scale. And then the question is, what is the suitable identification of this energy scale with some length scale? As I will tell you, there is no principle up to now what is the precise correspondence between this energy scale and length scale. This is a problem that I'm going to tell you. Before that, let me tell you about what is asymptotic safety. In this approach, we consider effective average action obtained by integrating out all fluctuations of the fields with momenta larger than k, which means that we define this W, which is path integral over the action with some source. And we introduce here some cutoff, which removes the most with energy less than the energy scale k. That means that we are integrating here all the most of energy scale k and larger than k. So, and this is, without this quantity, this is the usual definition of the one particle generating function of one particle, generating function of the connected Green functions. And then by making a Legendre transformation, you define the generating function of the one particle irreducible particles. And this, in principle, if without this cutoff, then this is the effective action which contains all the effect of quantum theory, because path integral is made over the whole scale. But here we are cutting off some most lower than the energy, some energy k. And in this case, because we are integrating over the high energy modes, this still contains a divergence coming from the UV modes. However, we want to look at the dependence of this effective average action, dependence on this energy scale k. And then we need to differentiate this effective average action by k. And usually we take this logarithmic derivative. Then it is possible to derive this general formula, which is very exact functional equation. And here is this gamma k is given by this second derivative of the field. And then you have a cutoff here. And here is a energy differentiation of the cutoff. Now, important point of this, we are just looking at how this effective average action is changing according to when we change the energy scale k. Then, if you look at this right-hand side, because this RK is introducing cutoff close to the energy scale k, and it is changing at the energy scale, and the other part, it doesn't change so much. That means the right-hand side is getting only the contribution close to the energy scale k. In this way, we get rid of the contribution of the high energy mode, so that this equation itself is well defined. You may think this is looks like a one loop approximation, but this is not actually the one loop approximation. In case of one loop approximation, you use only the bare action here, but here is actually full gamma, which means that this is you have to solve this equation consistently, but this is equation which is satisfied exactly by the full gammas. So if you can solve this equation exactly, then you get all the quantum effects included.
So what is the capital R sub K in delta?
This is a function which tells you how you cut off. And what you usually do is you introduce some a function depending on the case going like this, and in the UV limit, RK goes to 0, and in the infrared limit, it is removing the low energy modes from the action.
You say RK kills the UV mode or
RK kills the IR mode.
IR?
Yes.
Oh, IR mode. So it's zero below roughly.
No, well, total is like that. But this RK itself is low energy has a full function, and then high energy 0.
Is it like it gives you math term to the IR mode?
Yeah, that's right. Exactly. Yes. So that is the reason why this is still not well defined itself. So that we want to look at the K dependence of these gammas. And when formally, when K is sent to K equals 0, then this cutoff is not there no longer. So that this is a full beta gamma effective action.
I'm very slow, and it's a very basic question about the quantum field theory. Let's say, so delta SK, since you are integrating over all Q, all the momentum mode, so it will be only dependent on K.
No,
So what is the phi dependence in delta SK? Because you are integrating over phi, all the phi, right?
This means that all the modes of phi with energy scale K and larger are integrated, path integrated. This is a kind of formal expression, but and this phi is not just a scalar field, but all the quantum modes you should understand. Is it? So this is integrated over modes of energy scale K and beyond.
So let's say for the in the path integral T5 over T5, and if we think about some IR modes, momenta are lower than K, then the contribution is from S and also delta S. Am I right? While for the UV modes, it comes only from the S, usual S.
That's right. So UV modes are still contributing, and I cut off, if from the path integral, I cut off the low energy modes, just including like a mass kind of term for the infrared cutoff.
And then by Lagrange transform from W, you get the gamma. Then
if K is set to 0, then this is absent because the cutoff is not.
And then there's a usual
But the quick problem is we can derive an exact equation that gamma K satisfies, and then once you have this equation starting from certain value of K, giving the initial condition, you can integrate over up to the high energy, where you can check whether the theory makes sense in the high energy. And after that, you can go down to K equals 0 to get the full gamma, which includes all the quantum effects.
Can you do the opposite? suppressing the UV.
I think that is, in a sense, a kind of Wilson renormalization group. Wilson renormalization group, you introduce a cutoff and you consider this to be integrated over up to lambda cutoff. Then you look at how the action changes depending on this UV cutoff is moved. But basically, it is.
But that will not be relevant to asymptotic gravity.
Well, I think you can also do similar thing, but most people are using this approach because somehow this is easier to calculate.
So in the effective action gamma
Mm.
sub k, so gamma sub k, there is a divergence. We have to do some normalizations. But the line below, the reason why there is no divergence is because in the derivative with respect to k, all the UV modes are essentially k dependence is very negligible. So
That's right.
that's the main reason.
That's right. That is the key point of this equation.
Does the equation have some coupling dependence?
Oh, I'm coming to that. So the way how we analyze this system is we write the effective action as a collection of operators of y. Take some operators as much as possible, we consistent with a symmetry, and then this functional normalization group equation tells you how the coupling in front of this quantity changes when you change this momentum. So, and then from that equation, you have this derivative on the left-hand side in terms of log k, and then right-hand side, you calculate from the right-hand side, which is gives you what is called the beta function. So this relation means in terms of this explicit expression, this GI, then coupling constant is how it changes according to this energy scale K is sent. Then we set some initial condition at some point, this coefficient to such and such values, and then try to see how this grows, how this moves around in our space when we send this energy scale to infinity.
So why do you call it effective average action? So you are calling gamma sub k as an effective average action.
That's right. This is to discriminate with the effective action. This is not the effective action.
Right. So if we send k equal to 0,
Mm.
then it may be agreeing with the effective action.
We consider this agrees with effective action, yes.
Right.
Because no cutoff.
That's right. But why do you call average? Average over what?
This is making some average of this path integral is making the kind of average, yeah,
Average over
over the modes.
which mode? You will IR. Because in the gamma k is a functional of phi.
Gamma k itself, the definition is averaging over the UV modes. But it has a cutoff at k.
So gamma k, you didn't like the argument, but in the gamma k should be a functional of phi.
Yeah.
Phi, right?
And phi is the operator that makes this quantity.
Right, so it's okay. Yeah.
So in case of gravity, you consider like a unit operator which corresponds to the cosmological constant, and R, which is corresponding to the Einstein term, and so on. And but what you know is that this coefficient changes according to the energy scale you are studying. Then the question is, what is the behavior at when you send k equal to infinity, which corresponds to your Baer theory, and whether this theory makes sense or not is the question. And in general, it is moving around in the coupling space, and it is possible there is a fixed point, which means by which I mean that beta is vanishes at some point. If beta vanishes, then this GI no longer runs. It doesn't move around. It takes a fixed point value, and then whatever the energy scale you go to infinity, this coupling never diverges. In that way, this gamma k can be well defined in the UV ring. So the question is, the notion of the asymptotic safety is defined by this. If all dimensionless couplings go to finite fixed point value at the UV limit, then dimensionless physical quantities are well defined in the UV. And in addition, there are only finite number of the couplings. Then our theory is should be only defined by this coupling constant, which has a UV fixed point. And in this case, we can have a predictability because there are only finite number of operators that we use. And then this is what is called asymptotic safety. The reason of this name is come from the asymptotic freedom. Asymptotic freedom is a case when this fixed point is zero. And asymptotic safety is we are considering a finite non-trivial value that beta vanishes. And in case of asymptotic safety, it is almost trivial to know which kind of operators are necessary in order to define our theory. That is precisely the renormalizable interaction up to dimension 4 operators. Beyond that, these are giving the divergences, which doesn't have a fixed point in the beta function.
Question?
Yes.
So if we consider this criteria in phi core theory, we know that it's not renormalized.
Yeah.
And maybe some conditions are not satisfied.
Yes. There is no fixed point if you consider lambda phi 4 theory. It diverges, and so in order to make this sense, you have to start to very small one, and when you go further high energy, this always diverges, and eventually you have to set this equal to 0, so that there is no interaction in your theory. And this is, in this sense, we are not relying on the perturbation, but non-perturbatively, if we can find such a theory, then we call this non-perturbatively renormalizable theory. And in this case, we don't claim that there is no divergence. There is a divergence, but like a Newton like a dimension for coupling has a cutoff dependence proportional to lambda to some power, and this diverges. But the important thing is when this is when the dimensionless coupling in front of this, if you look at this and this goes to a finite value and never diverges. So if you just make a dimensionless combination out of this is always predictable quantity. And in this sense, all the coupling of dimension scale as just as its dimension. In this sense, there is a scaling invariance theory. Whatever the energy scale is, if you 2 times make the energy scale larger, then this is just simply some coefficient in front of this to the power of this cutoff. And in this sense, the theory has a scaling invariant. This is the most important part of this approach. And in this point, I think there may be some connection with string theory, but connection with string theory is not yet understood. And so once we identify what is a UV complete theory by identifying our theory, then we can integrate down to k equal to 0 to get the full quantum effective action. And you can check what the quantum effect is. And there is no divergence we expect because UV divergence is already under the control. And now we are not trying to derive the full effective action, but trying to find some effect coming from the fact that the coupling constant depends on the energy scale. And in particular, in case of gravity, we are looking at the energy dependence of Newton coupling, how it affects our geometry and our understanding.
So in the case of k equal to 0, since it is usually effective action, the local operators that you expanded your gammas of k, it's essentially some some polynomial of phi or derivative of phi, some power or like that usual thing.
Yeah.
And up to some lower powers, those are renormalizable. But there may be infinite series. Most of them are non-renormalizable. So what you're saying is that those will be kind of irrelevant and so will not contribute in your argument.
That is a very important point, which, as far as I understand, is not fully understood yet. But our hope is that, so what do we do in reality? In principle, you have to include all the operators, which is consistent with symmetry and symmetries. Yeah. And then we check what is the beta function of these operators. And then try to find if there is any fixed point. And if there is a fixed point, we have to see if this is a UV attractive fixed point. If it is not a UV attractive fixed point, it simply diverges. So we want to get rid of such an operator. We want to just have operators with UV attractive fixed point.
This is imposing asymptotic safety.
That's right. And this is okay because this is just like in perturbation, you exclude the dimension higher than 4. And these are irrelevant operator in this sense. But in this case, it's not that trivial. Dimension may not be the only criterion that the fixed point is a good one or not. You have to really calculate beta function, check whether there is a non-trivial fixed point. And in case of non-trivial fixed point, there is a possibility that there is this could be attractive or repulsive in the UV limit. So this is very complicated. As far as I know, this study has been done up to curvature cubic theory. And curvature cubic term is now found to be irrelevant, so that we don't have to consider that. Quadratic term, there is some debate about this, and there may possibly just one combination of quadratic term which is relevant, but there is another argument that this kind of quadratic term can get rid of by using a field equation or just by field redefinition. If we can get rid of such a quantity by field redefinition, these are redundant operators and we can throw away this. Yeah. But final understanding is, I think, not yet obtained. And in addition, this is only understood only when we have pure gravity theory, and when matter comes into, then you have to do similar analysis again to identify what should be your whole theory. And I'm trying to understand it by including scalar field in this case. Anyway, so this is the whole picture of asymptotic safety to quantum gravity. So, and for simplicity in this talk, I'm just considering the Einstein theory with the cosmological constant. But when the cosmological constant is included, this has a very bad behavior in the UV limit. So we just simply assume that cosmological constant is 0 or extremely small, so that we can forget about the running of this quantity. And in this case, we can make some approximation to solve the renormalization group equation for the Newton coupling. And it turned out when it is made dimensionless quantity, this has this form. in terms of K. Tilde means that this is some Newton coupling at some energy scale, and this has a mass -2 power dimension full, so that if I multiply it by K square, this comes as a dimensionless quantity. And it turned out that this dimensionless quantity has a finite fixed point in the UV limit. And you can see that if you send K equal infinity, then this one can be ignored. This GK square cancel each other, so that the UV fixed point is 1 over omega, right? So Newton constant is not diverging, but it is going to finite fixed point, not zero fixed point, but finite quantity. When translated it into the dimension for Newton constant, it is given by this. Then it is interesting to notice that when K sent to 0, then sent to infinity, this Newton constant is vanishing, which means in the high energy limit, gravitational coupling is becoming weaker and weaker. So this is the picture that we get from this asymmetric safety approach. Then we want to apply this the energy dependence to the black hole. So naturally, the K has an energy scale, and if we try to relate this to some distance scale, this should be inversely proportional due to the Broglie relation. We refer to identify this quantity, and psi is some number, dimensionless number of order 1.
Because coupling and energy high energy means that at high energy there's no gravity.
Gravity is vanishing, but not really vanish. This is an infinite limit, and you don't go to infinite limit, right? In some finite value, like say energy scale, then you still have some gravity, but it is becoming weaker. Yes, right.
Much weaker.
Right. Otherwise, because mass becomes diverges, so that it looks like a gravity becomes too strong. This is a part of the picture. But if you consider the renormalization group, the G is vanishing, so that this compensates this increase of the mass in the high energy.
Remove that effect. Could you remove the singularity also?
That is the point that I'm going to tell you. Yeah, just a moment. Okay. And we claim that it is possible to some extent, but precisely speaking, this is just a possibility. Anyway, so we have to identify what is this D is, and we want to make this just like a coordinate, but something that it doesn't depend on the coordinate. So first suggestion was made to use the geodesic distance from the origin. And take the example of Schwarzschild black hole. This is given by this metric, and this is the quantity. And if you calculate the geodesic distance at R, then for R larger than the horizon length, then it has this value. And if R less than the horizon, then it takes this value. The interesting point is that when you check R goes to infinity limit, then this geodesic distance close to R, simply R, so that this behavior is classical behavior is recovered, and also then in the short distance, D is vanishing like this. This is the reflection of that when K goes to infinity, that Newton coupling goes to 0. And then Newton coupling is given by this square, so that this is R to the third power vanishing in this case.
But if geodesic is what, timeline, or it cannot be known, like,
We take just absolute value and square root of this.
but you should specify whether it's timeline or.
Yeah. In this case, we just take absolute value and define by this
That
quantity.
is a spatial like geodesic, not physical, not physical geodesic. So, I guess you just meant proper distance.
No, but you see, this is when at a fixed time, then this is the metric that you have for your space time.
Proper distance,
Mhm.
just proper
Mhm.
distance,
Mhm.
but space like
Mhm.
separated.
Yeah, outside the horizon, you are okay with this. Inside the horizon, well,
You change it to the
yeah.
time coordinate.
We just take the absolute value of this quantity.
Second term again.
Hmm?
Second term, not the first term. You don't switch depending on whether you are outside, inside.
Actually, so what we do is just to take this absolute value of this and calculate the.
Both of them, outside and inside. You know, inside the T becomes space like, so I'm asking whether you
Yeah,
change it.
yeah. We are just regarding this time, and this is a distance, and then you see r less than 2g0n, this has to be positive, which means r is this inside, we just use this quantity. Well, actually, this is not our proposal, but their proposal. And actually, we are going to propose a different thing.
What is the G naught? Is it there?
Denote is just a bare one, which
At the infinity,
say zero energy.
at the
G-
zero energy.
G0 is this quantity, and this is the some reference energy scale. So you see, if you set k equals 0, then it is gk0, and this is zero energy Newton constant. This doesn't have really energy dependence, but just a constant. So when you set some energy scale here and measure this quantity and identify by experiment.
For instance, we can say that there's a classical level of Newton constant.
So though the identification might still strange, but this has an interesting implication. So as I told you that the GR is asymptotic behavior is given by like this when r goes to 0. So in this case, the function f in the metric goes to 1 because it is 1 minus 2gm divided by r. And depending on how mass is the behavior of this function f changes. If when there is no quantum correction, this is a line that you find. So this is going to minus infinity, which means that you have a singularity.
So where do you get this power I to the cube?
Hmm?
The power I to the 3.
That is from geodesic distance. So you calculate this geodesic distance from this, and then check how it is behaving in the short distance. Then you see that this is arc tangent. When r is small, this is square root r, and then that square root r is subtracted by this. So the next order is r to the 3/2.
And then you replace your momentum equation by this GR equal, including this square.
Yeah. This square is actually originally it was psi square over d square here, but I just multiply this.
You replace A by one over D.
Yeah, right, basically psi over d.
But do you make any connection to Browns decay?
Browns decay.
Yeah, after all, your complete constant, Newton constant become position dependent.
Ah, it is possible to make that, but that is when you want to consider action. This is something that you have to consider, but simply this is just obtained by at the solution level, we make this approximation. It is another question whether there is any field equation that this solution satisfies or not.
So how do you get the G? I mean, I'd like to have some analogy with the, let's say, QCD coupling. Usually one may calculate one loop order, and then we have some running coupling. Then we integrate, and then can get some similar formula, right? And we can show, I mean, where. So that kind of argument, is it like that, or how did you get there?
Exactly. This is by integrating the renormalization group equation. You know, dGdt equal beta, and we integrate this.
And the beta function you evaluate at one loop in the quantum?
Basically, I may say one loop, but this includes renormalization group improvement, which means you have lots of bubbles included, summed over. Yes, that is reflected by this kind of factor, you know, in the numerator. If you expand this, then you have the expansion in terms of G. But this is not just, then this is summed over by the renormalization.
This is not a full non-perturbable result.
Yeah. If you want to have an exact expression, this is
Okay. So
this is a leading order approximation in the sense of you know, the ladder type and that kind of thing. This is used only like in QCD too. So yeah, here, I'm sorry. I probably I can't reach to the point that what I did. 15 minutes are left. But okay, anyway, it's better not to reach, but better for you to understand what is this approach. And so when mass is large, we have this kind of behavior that this has to go to 1, yeah, to R equals 0, but it comes like down, try to mimic the classical case, and then, but eventually quantum vector dominates, and so that it has 2 horizons in this case. Then if the mass becomes a little smaller, then this looks like an extremal solution. Then if mass becomes further smaller, then quantum effects dominates over the classical behavior, and it doesn't have any horizon. So this suggests that if you start from a heavy black hole, then by Hawking radiation, it emits radiation, it loses mass, then it becomes smaller, this shrinks, and when it attains this extremal case, then it no longer radiates. So this already suggests that the Hawking radiation will stop at some point, and there will be remnant. This is how this approach says something to the Hawking radiation. It never evaporates in this approach completely. And because of this, you may think the singularity of the origin may be resolved, but this is just conjecture at this point, because we don't know if the relation is really like that.
So what you're saying is that usually in the short-lived black hole, then heat capacity is negative, And usually we understand that that's a thermally unstable. But what you're saying is that this quantum effect will cure so that the heat capacity will change its sign to positive quantity or heat capacity.
In terms of heat.
So I guess, I mean, unlike in the ADS, where we have two branches, large, so in addition to the small black hole, we have some large black hole branch, which appears newly, and these large black holes are stable thermally because heat capacity is constant, while small black hole side, which is essentially the part corresponding to the Schwarzschild black hole, there is a negative, so we interpret it as a thermally unstable. But my question is whether you are claiming that the quantum effect will cure that. So
Designed the ADS black hole.
in the ADS, a large black hole is stable, but small black hole is not. But the Schwarzschild case is the extreme case that is a really small black hole branch,
Yeah.
which is well known that it's unstable.
Question is when the quantum due to the quantum effect, if the has a two horizon, it very similar to the light bulbs.
That's right, that's right. Yes. Yes.
So
It is very similar to.
I see. That's
yeah.
This kind of approach is also can be extended to rational North flow solution, but basically the behavior is similar. And up to this point, it looks like good, but there still remains. If really this kind of identification is necessary one or not, nobody knows, no criterion. Just to make a dimensional grants, you may make identification. But is it true? And in fact, there is another identification proposed, like using some Kretschmann invariant. Why not use? If you use this Kretschmann invariant, you get a different behavior, though the point of singularity resolution doesn't change. So this is the question that we are interested in, and we also try to extend this to a Kerr black hole solution. Then it turned out there is some, at least to some extent, there is a criterion that has to be satisfied. And so, okay, I can make a long story short. First, there is some approach to the Kerr solution, how to identify the length and energy scale. And in one approach, they make an identification of choosing geodesics at a fixed angle. Because the Kerr solution doesn't have a spherical symmetry, in order to define the geodesic distance, you have to define some angle. And then they give a similar argument, but such a analysis depends on the angle, and how can we understand what is such a approach makes sense? Then do we have to include the angle dependence to more general case? Then it turned out if you include the angular dependence, then surface gravity, which should be related to the temperature of the black hole, depends on the angle, so that on the horizon, the temperature changes, so that there is no sense of thermodynamics. Another problem is if we include angular dependence into G, then the scalar curvature, if you simply calculate the scalar curvature from the metric, then you find that there is this factor of delta, which determines the place of the horizon. Delta equal to 0 is the condition to determine the horizon. This means that if we have a theta dependence on G, then this gives me a divergence at the horizon. So this is not, again, indication that there should not be angle dependence. Now,
I have very simple question.
Hmm?
When the Newtonian constant and also the R and zeta, so you obtain the Einstein equation from the variation of the action.
no, we are not looking at the equation. At the moment, we just substitute this quantity and study the property. Your question is very important in the sense that if you have an action and field equation, this is a more general formulation that can be applied to other cases. But we are just starting this analysis by just looking at the equation, because this is much simpler than to solve the field equations. Yeah, there is some limitation, I agree, but yeah. So the correct identification is not clear at this point. And then what we propose is that we must impose the consistency condition of the first law of thermodynamics as a physical guiding principle, at least near the horizon. The reason why I say near the horizon is thermodynamics is defined on the horizon. Okay, so what is the idea? So first law of black hole is given by this in case of rotating solution. Here omega is the angular parameter and J is angular momentum. So we have to keep this relation valid even at the quantum level, because this is related to the energy conservation. Now, instead of using mass as our independent variable, we use this outer horizon radius to be our variable, because mass is determined by this condition, delta vanishes this, and then assuming G doesn't depend on M is determined by this. Given R plus, M is determined. And I also include A, because here A is becoming a variable. And then this quantity is already known, and M is also known, and T can be calculated from the surface gravity, and it has this complicated expression. Then all the quantity has a dependence on R plus and A, so each variation has this form, and then comparing the coefficient of dr plus and dA, you can easily get from this equation what is the derivative of S with respect to R plus, and this is given by this, and the A derivative is given by this. Then we already know what the M is in terms of R plus and A, J and omega, everything is known. So you have a right-hand expression already. The question is whether this is actually integrable system or not. If it is integrable system, then we have to have this integrability condition. It turned out that this is quite non-trivial equation. The concrete expression we get is this part is very simple. This part is extremely complicated. But when we plug this into the integrability condition, it turned out it can be simplified into this form, very simple looking form. But it is difficult to solve this in general because this is the differential equation. We just look at this part. Then it is immediately clear this if G is a function of R plus square plus A square, then this is trivially satisfied. This is the simplest solution to this equation. So we just take this and then plug, and in fact, this is a horizon area in case of Kerr solution. If you multiply 4 pi, and then if you plug this relation that G is a function of A, then this complicated looking expression boils down to this simple expression. Then, because this satisfies the integrability condition, you can simply integrate either of this equation to get this formula, which is dA integration over A divided by 4GA. G is a function of A. And it turned out this is quite a general form. And the one evidence of the correct, this is correct, is that when G is a constant, same classical case, this reproduces the Bekenstein-Hawking formula, A divided by 4G. And we check other solutions, and of course, Schwarzschild black hole is given by setting A equal to 0, and the formula is valid. And 5-dimensional Meyer-Sperry black holes with 2 angular momenta, we find that that formula also valid, and so on. And in many examples, we find this formula is valid. Very good, imposing first law of thermodynamics. And to get some idea, let's take a simple example that K is given by psi divided by square root of A. And up to 4 pi, square root of 4 pi, this is this, and plug this into the expression G. This is the formula for this, and in fact, this is a function of area. And if you integrate this, you get to this equation. Then you see that in addition to the Bekenstein-Hawking formula, you get some correction from the quantum term. Logarithmic term is known to be obtained by some quantum effects. So then, this is all on the horizon, but it is natural to extend out away from the horizon. Then this means that K is a function of R squared plus A squared. And then G is a function of R squared plus A squared. However, it is clear that there is a singularity at R equals 0, right? If you set to R equals 0, then this R squared plus A squared never vanishes or diverges. This means that you cannot remove the singularity by this identification. So there is still something missing in this story. And that is the point that I have to finish in one minute. And fact is that then look at this condition for the horizon. It actually involves an M here, and this relation means MR plus is a function of area. And then we should think that the general identification could include mass dependence. And in fact, the geodesic distance actually included mass in the geodesic distance. So it is natural to also include the mass dependence. So suppose that G also depends in addition to R plus A and M. Then the consistency condition, when you check out this, then this boils down to this equation, then it is immediately clear that G must be a function of area first. Looking at this part, you can identify this part cancel if G is a function of this quantity, and then this quantity and this quantity cancel with each other by including this dependence as well. Of course, on the horizon, there is this relation, so that you might think that this is actually the function of area, but in fact, we can just say that this G can depend on area through MR plus dependence. This is important when you extend this away from the horizon. And including this mass dependence, it turns out that the entropy formula is modified like this.
So you mean the R plus A and the M all are independent?
On the horizon, they are not actually independent, but formally, this consistency condition can be satisfied. If you just forget about this relation, this could be a function of this and this quantity. This is important when you go away from the. So what I want to say is that this is consistent with our previous analysis, but we can say that G can depend on the area through this quantity and this quantity directly. this is important when we move away from the horizon, because we are going to move R plus 2 into R. Then one possibility of choice is given by this. We want to have a case where this quantity goes to infinity when R sent to 0. So it is better we can have this quantity, but it turned out in this case, because in the expression of Newton constant, there is a G0 multiplying this quantity, so that the Planck scale is going to be absent in the quantum effects. And this is pointed out by a referee that such a identification shouldn't be made in the gravitational theory. Then it turned out that we could have another identification. Oh, didn't I write it? Oh. And that already have a good behavior, and that is this identification is still on the archive, but we revise our paper to not to include G0 in the identification. And in this case, you can easily check that the Planck energy scale is coming into the plane, and this is we think a better identification. And as long as P we choose P larger than 3, then this is vanishing to the R to the 4th power if you choose P. And this is going to eliminate the singularity. And in fact, when we calculate the scalar curvature, when theta not equal pi over 2, then this has this power, and when theta equal pi over 2, this has this power. So P equals 3 is a little bit subtle. The P equals 3 case, this is finite, this is vanishes at R equals 0. So P equals 3 probably not good. And similarly, another Fritzman invariant has similar behavior. So we think physically desirable choice is P equals 4. And this is a minimal value for the property to remove the singularity. And so, but as you can see, we give some criterion to make identification. And it is good in the sense that surface area of horizon has to come into the game, but we need further precise identification. At that point, we don't have any criteria yet. So this is still a subject to be studied, but at least we have one strong constraint that it has to be a function of this area and MR. So this is the point that I have, and 5 minutes already over. But this is just a summary of what I told you. Thank you very much.
I have a question about, so you focus on the Einstein gravity for now. Then we all know that the Einstein gravity by itself is non-renormalizable.
Yes.
And the approach you mentioned in the beginning, adding this RK term, it gives you mass per IR mode, not the UV mode. So in some sense, it cannot cure the fundamental issue in Einstein gravity regarding this non-renormalizability, right? Because the UV mode is always, the UV divergence is the problem in G Newton. So in some sense, this procedure cannot resolve the original non-renormalizability of Newton constant, right?
Okay. What I think now is like this. You start with Einstein gravity and calculate, and then we calculate this renormalization group equation and find there is R square and that kind of term generated on the right-hand side. But these are redundant operators that I can remove. by changing the field. Field redefinition can remove R square and R mu square.
But then you're saying Einstein gravity can be made normalizable just by field redefinition?
That's right, that's right. And then and this is already known since the Tufts-Bertman made a perturbative calculation of gravity. What they do is start with Einstein gravity and then calculate the one loop correction. They find the R square term and the R mu square term generated. But these terms can be eliminated by using a field equation, which means these terms can be eliminated by the field redefinition. So at that point, it was not clear whether the Einstein theory is renormalizable or not. Now, then there is a guy, the Italian guy, doing a two-loop calculation. They find at a two-loop level, Riemann curvature cubic term appears with a divergence. But this term cannot be removed by the field redefinition. So this is the end of the Einstein theory. It was solved. Now in this, and this is, by the way, Goroff-Zanotti. Goroff-Zanotti's work is very famous in the sense that Einstein gravity is not renormalizable. They showed for the first time by calculating two-loop effect divergence. Now, what we find now is the coefficient of this. There is a beta function that you should calculate to this. The beta function turned out to be showing that this is a UV repulsive fixed point they have, which means in this approach we have to remove such a kind of term in your theory. So I think at the moment, what I say that we can just consider this Einstein theory plus cosmological constant, but already at the Tufts-Bertman case, they also calculated what happens. So a pure Einstein gravity is okay, but they also calculate when a scalar field is included, they find another divergence which cannot be removed by field definition. So this is a point still not studied. So we have to study if this kind of approach makes sense in such a case. And that is a thing that I am trying to work on now.
Could you give some comments about holography
Holography.
in Europe?
I'm
At the
sorry.
nightmare level,
I'm sorry.
inconsistent with the holography. Because you need
It
to
is
visual better.
yeah,
Newton constant in
holography.
next to the 1 over n in the Yang side.
This energy scale might be related to the when you consider holography, you have an extra dimension or not. Yeah, it might be related to that, but I'm sorry, I don't know. It's left for you.
Very nice question. So I thought the quantum effect of the gravity may be important. That's what usually people think of if the energy scale is order of Planck energy or more. And typical black holes. So does it mean that you are talking about the distance d or all the things in a very like the tiny one or?
Yes, the region the quantum effect appears is close to the Planck scale. So basically, I should divide this here, and then you see that G0 is divided by this quantity. When the quantum effects becomes large, which means that this quantity must be larger than G0. So this means that beyond the Planck scale, the quantum effect is becoming strong. Lower than that, quantum effect is not strong. Yeah, that kind of thing happens.
So
And actually, this is a point that the referee pointed out. in the previous
So we
identification.
observed through the gravitational wave some merger of the black holes that we believe is coming from the merger of the black hole. Are there any some similarity inside or not? Because the black holes are very large, right? So it's in terms of distance or anyone is a much bigger scale, the lower energy than the Planck scale.
If you consider very big black hole, then quantum effects is very weak. You have to go to near the singularity to see the effect of
I see,
quantum.
even in the case then the inside the horizon. Yeah.
You know, the big black hole has a very weak gravity on the near the horizon, and this is well approximated by the classical picture.
So in your formula, the R should be very close to the singularity.
Well, we are thinking this is valid for energy range, but yeah. Especially the quantum effects is strong when they close to the Planck scale.
So actually you are considering just considering singularity at the origin. So, but I think that there appear another kind of singularity that is, as you know, horizon singularity. Actually, horizon singularity may be regarded as only singularity, but from the point of view of fixed observer, actually, UV divers appear, as you know, black hole entropy, the origin of entropy comes from the area at the horizon due to the UV divers. Cut off the UV divers, you can get a finite entropy. So in that sense, instead of actually, additionally, R equals 0, actually R equals 2gm would be important to apply your idea.
But yeah, to say this is a coordinate singularity, and if you use different coordinate system, you can get rid of
Fixed
singularity.
observer, from the point of fixed observer. Actually, you are considering just a freely falling observer by calculating the top line. So instead, actually, you consider fixed observer near the horizon.
Actually, we are not planning to use a proper distance, but we still don't know how to make a precise identification. We are just saying that this identification must be through this horizon area and other quantity. To specify more than that, we need other physical criteria. Maybe what you are saying might be another criteria, but I think horizon singularity is not really physical.
Physics depends on the observer.
Yeah, but that is something contradicting to the spirit of general covariance. Whatever the coordinate system, you should get the same physical picture.
For the identification, can you do some brute force Fourier transformation of your effective average action towards from the momentum space to the forward?
That you have to calculate this effective action down to k from 0. And in general, you create lots of non-local terms as well as local terms. And if you consider flat space-time, then you can make a Fourier transform, but I'm not sure when it is in the curved space. This approach can be used for any kind of background. But yeah, studying effective action is an interesting subject that should be studied more, because there are very few work studying this kind of thing, and what the physical consequences from this approach are not so much studied.
somewhat related but a different expression. So it seems that in your former part of the asymptotic safety, the function choice of R, which is more or less time below the scale K, and which is vanishing also in the UV region. So it seems to me very what is the so how much sensitive is in the argument? So the detail of the R is not important.
Sensitive with
Yes, the choice of the delta.
well,
And of course, since it's almost like a step function, of course, it is very the most dominant when you take.
you are asking cutoff dependence in this approach.
K, yeah.
I think there are some cutoff dependence, but qualitative behavior that there exists a fixed point for this Einstein Newton constant is universal. Any approach, they find a fixed point, finite fixed point value. In fact, G equals 0 is also a solution, but there is additional fixed point non-vanishing.
Other questions?
If you don't claim that actually space line time, in connection with this question, I have a similar question. For instance, R equals 0 means actually T equals 0.
No, we are
inside,
just looking at the T equals 0 or T fixed value of T time slice and then try to calculate the geodesic distance. Yeah, in fact, inside the black hole, the sign changes, but we just consider this in terms of the absolute value.
Have you given more comments about the entropy change in your approach?
Entropy
change, low correction. Did it always something in your approach?
sign. You're asking about the coefficient of this log term.
It always something for
That is a positive. This omega tilde is positive.
do you have any interesting explanation for that?
No. Omega is something that calculated in the equation, renormalization group equation. This is like 1 over 4 pi, something like that. And pi is positive, so the coefficient is apparently positive. And what does that mean? Entropy is increased by the quantum effects. I'm not sure. Maybe this indicates that there are more degrees of freedom at the quantum level.
Log term can be either positive or negative, depending on the size of the argument, right? So usually, or in other words, there must be some
divided by
divided by some factor dimension.
that part we don't know, because what we get is just a differential equation or derivative. So there probably that should be determined by the first zeroth law of thermodynamics. The entropy should take 0 in the very low temperature related thing. But yeah.
There also random over there. It means entropy may be 0 at some scale for R plus. So in that sense, I'm not sure whether low.
Well, I think that is a logarithmic term, so that power of R plus square plus A square always dominates. And
the smallest entropy should be 0 at the when the remnant entropy is zero, because the single state is single. So each log number of state is log 1 is 0, entropy is 0, which means that the log fraction should be negative.
There is a Wittgenstein-Einstein term.
And plus the positive and log fraction may be negative. Cancel out the Wittgenstein eventually.
May depend on the quantity dividing the inside the log. Yes.
So that formula seems to say that for very tiny quantities, entropy can even be negative. Because I mean, if A is also very small and the R plus is very small, then it's more negligible than the logarithm term. And the logarithm term, depending on the some scale, the denominator.
Okay, we are talking about a very small thing. At least what is clear is Garcia case is first term is dominating so that it doesn't change sign. When it becomes smaller, that
The small scale is where quantum effect should be more important.
What is the random limit? If we take the random limit, remnant, you just talk about the remnant.
remnant.
So remnant means
Remnant is
state.
temperature zero case. Temperature
Small r plus actually negligible a, actually negative contribution from no correction. So
I think at the zero temperature, it should be positive. I haven't checked, but that is should be calculated from the temperature expression of the temperature. Where is that? Temperature equal to zero. Yeah. Okay. That's what I have to check. But I suppose there is no vision that entropy becomes negative because it corresponds to the degrees of freedom.
Dimension-wise, your log sum should be, I mean, inside this argument should be dimension depth. And there should be, I think, 1 over G 0.
Dimension. Yeah, we can just add some additional.
G0 should be there. Then it's Planck length scale. So the small limit is smaller than Planck length.
If it is G0, this is something like x plus rho x. I think dividing this quantity should be some boundary condition, some reference point that I have to look, and it may not be necessarily G0. Yeah, that I'm not so sure, but doesn't have. I think it doesn't have to be a G0, but could be something different.
Actually, you can compare typical correction or Rn type or Hayward type.
Hayward.
I think they actually negative low correction.
Negative entropy. Negative entropy. They have. Do they have that?
Consider remnant,
Gravity, remnant,
consider remnant,
graviton.
the entropy goes to zero at some scale
Uh-huh.
of remnant size. It means if you
No, temperature goes to zero, but
Zero.
doesn't mean necessarily mean
so
entropy
it means
zero.
alpha goes to getting smaller and smaller, then actually there are confusion at some scale.
As a physical process, it cannot go below that
It
extreme
depends on the
case.
size of alpha anyway. So this question is talking about always negative. I think it depends on the size.
I mean, this, yeah, well, I think, yeah, what quantity should come into this row, it's not clear at the moment. Both, yes. So,
So if there is no question, then President again, the professor will mention.